Look at your hand. Go ahead. Actually look at it. 5 fingers, skin, the little lines in your knuckles. That hand is made of atoms. You know that. Each atom has electrons orbiting a nucleus. You've heard that too. Your hand alone contains something like 10^28 electrons. That's 10 million trillion. A number so large it stops meaning anything concrete. Now here's what John Wheeler told me one afternoon, and I have to be honest with you. My first reaction was that he had finally lost his mind. Wheeler was my doctoral advisor at Princeton. Brilliant man, the kind of physicist who isn't afraid to say something so strange it makes you uncomfortable. And in 1940 he called me on the telephone and said, "Feynman, I know why all electrons have the same charge and the same mass." I said, "Why?" He said, "Because they're all the same electron." I want to be careful here because this idea is either one of the most profound things in physics or an elaborate thought experiment that happens to be wrong in several checkable ways. And I'll tell you exactly where it goes wrong, which is itself interesting. But let's start with why Wheeler thought this at all, because that's where the real physics lives. Here's the problem Wheeler was actually solving. Every electron in the universe, every single one, has exactly the same mass, 9^109 x 10^31 kilograms. Exactly, not approximately, not almost. Identical to every other electron anywhere. Same charge, negative 1.602 x 10^19 coulombs. Same spin, same magnetic moment. Every electron is, for all physical purposes, absolutely interchangeable with every other electron. Why? That's not obvious. It demands an explanation. In everyday life, things that look the same are copies, manufactured to a tolerance. But electrons aren't manufactured. They weren't stamped out by some cosmic factory trying to meet specifications. So why are they identical? What enforces this? One answer, Wheeler's answer. They're literally the same object. To understand what that means, I need to tell you something about how we describe particles in quantum field theory. Because when physicists say an electron travels from point A to point B, they mean something very specific. They mean a path exists in space-time, with time as one of the 4 dimensions. A moving electron traces a line through this 4-dimensional space, what we call a world line. You can draw it as a squiggly line going forward in time, left to right. Now, you know from special relativity, from Dirac's equation specifically, that for every particle, there's an antiparticle. The electron's antiparticle is the positron. Same mass, opposite charge. When an electron and positron meet, they annihilate. Both disappear, producing 2 gamma-ray photons. Here's the thing Dirac figured out, and it's one of the most beautiful reframings in physics. A positron moving forward in time is mathematically identical to an electron moving backward in time. Let that sit for a moment, because I know your instinct is to dismiss it. Moving backward in time sounds like science fiction, and I understand that. But this isn't metaphor. It's in the equations. When you write down the quantum field theory correctly, the amplitude for an electron propagating forward in time is the same as the amplitude for a positron propagating backward in time. They're the same term. We can't distinguish them mathematically. Wheeler put these 2 things together. If an electron can effectively travel backward in time and appearing to us as a positron, then a single electron could, in principle, trace a path through all of space-time that zigzags. Forward in time for a while, then backward, then forward again. Each forward segment would appear to us as an electron. Each backward segment would appear to us as a positron. If the path zigzags enough times across the entire history of the universe, a single electron could account for every apparent electron and positron we observe. One electron, stitching through space-time like thread through fabric. What we perceive as 10^80 electrons, our best estimate for the number in the observable universe, would be 1 electron visiting 10^80 different moments. Now, I want to show you why this picture is not crazy on its face, why it's actually a reasonable consequence of things we know, and then I want to show you where it goes wrong. First, why not crazy? The path integral. In 1948, I developed a formulation of quantum mechanics that Wheeler himself had pushed me toward. Instead of saying a particle takes a definite path from here to there, you sum over all possible paths. Every conceivable trajectory through space and time, no matter how bizarre, contributes an amplitude. The actual probability is calculated by adding these amplitudes together. Constructive and destructive interference determines what we observe. What this means is that space-time paths in quantum mechanics are not just visualization tools. They're what the theory is built on, and nothing in that framework says a path has to go monotonically forward in time. The math doesn't require it. When you allow paths that double back, electrons turning into positrons and back again, the technical name is pair creation and annihilation, you get quantum electrodynamics, QED, the most precisely tested theory in the history of science. It predicts the electron's magnetic moment to 11 decimal places of accuracy. The zigzag paths are real. They contribute to calculations. We couldn't get the right answers without them. What Wheeler was saying is, maybe the most extreme version of this is literally true. Maybe the universe has one path that zigzags through all of time. Okay, where does it fail? I told Wheeler when he first proposed this, if there's one electron visiting each moment, then whenever it turns around in time, an electron turning into a positron, that creates a pair, an electron going forward and a positron going backward. And whenever it turns around again, that destroys a pair. So the number of electrons in the universe should roughly equal the number of positrons. We look around and the universe is made almost entirely of matter, not antimatter. Electrons vastly outnumber positrons. This is actually one of the deepest unsolved problems in cosmology. Why is there more matter than antimatter? It even has a name, baryon asymmetry, and we don't know the answer. But whatever the answer is, the lopsidedness of matter versus antimatter is a direct empirical challenge to the one-electron hypothesis in its literal form. Wheeler's response to this, when I raised it, was something like, maybe most of the positron segments are hidden inside black holes or before the Big Bang. This is, I will be honest with you, not a satisfying answer. Hidden somewhere we can't look is how you rescue a theory that isn't working. So the one-electron universe is probably wrong as a literal description of physics. But here's what it tells us that is deeply true. The question Wheeler was really asking, why are all electrons identical, has a real answer. And the answer comes from quantum field theory. Electrons are not little balls with properties. An electron is an excitation of a field. There is one electron field spread through all of space-time. What we call an electron is a localized disturbance in that field, the same way a water wave is a disturbance in water. When you have multiple waves on the same body of water, they're not independent objects. They're excitations of the same medium. This is why every electron is identical. They're all manifestations of the same underlying field. The field has certain properties, it obeys certain equations, and every excitation of that field inherits those properties exactly. It's not that electrons are copies of each other, it's that electron refers to the field, and individual electrons are what happens when the field gets locally excited. This changes what you should picture when you look at your hand. Those 10.28 electrons aren't particles sitting in the atom the way planets sit around a sun. That picture is wrong, useful for some purposes, but wrong. What you have is a region where the electron field has high amplitude, concentrated near atomic nuclei. The field extends everywhere, in your hand, in the air around you, in the empty space between galaxies, everywhere. And not just the electron field. The quark field, the photon field, the Higgs field. Every particle type is a field, and those fields overlap everywhere in space simultaneously. What we call matter and empty space are both regions of these fields. Matter is just where certain fields have high excitation density. I want to make this concrete because I know fields can sound abstract. When you look at a neon sign and see red light, what happened is this. An electron in a neon atom was in a high energy state. It dropped to a lower energy state. The energy difference, exactly 1.96 electron volts, was deposited into the electromagnetic field. That excitation propagated outward at 299,792,458 meters per second. When it hit the cells in your retina, it was absorbed. A rhodopsin molecule absorbed that field excitation and triggered a nerve signal. At no point did a little particle fly from the neon to your eye. What happened is a disturbance traveled through a field, the same disturbance that constitutes light and radio waves and X-rays and the force between magnets. One field, different frequencies of excitation. Wheeler's one-electron universe, even in its failed form, is pointing at something real, the deep unity behind the apparent multiplicity. The apparent billions upon billions of separate particles dissolves when you describe things correctly, and you find fields, a small number of fields, whose behavior generates everything we see. Now let me push this further, because I think most explanations stop too early. You and I are in the same electron field, The electron field in your body and the electron field in my body. They're not separate fields. They're the same field at different locations. There is no seam between them, no boundary where your electron field ends, and my electron field begins. The field is continuous through all of space. What this means is that, in a precise technical sense, you are not a collection of particles. You are a configuration of fields. A particular excitation pattern, complicated, yes, enormously complicated, but a pattern in something that extends everywhere. The electron field in your hand and the electron field in a star 400 light-years away. Same field, different amplitudes, connected mathematically in the same equations. The Pauli exclusion principle, the fact that no two electrons can occupy the same quantum state, enforces itself across all of space simultaneously. Every electron in the universe knows about every other electron's state, not through any signaling, but because they're all the same field, and the field's constraints are global. This is weird. I know it's weird. I'm not going to soften it for you by saying, well, for practical purposes, because I think understanding why it's weird is more important than being comfortable. Here is an experimental fact that makes this concrete. Take two electrons that have interacted in the past. They've been entangled. Separate them by any distance you like, a meter, a kilometer. In principle, light years. Measure a property of one electron. Its spin, say. Instantaneously, and I mean instantaneously, not very quickly, instantaneously, the other electron's complementary property is determined. This is not a theory, this is an experimental result. Alain Aspect measured this in 1982 in Paris. John Clauser measured it before that. Many groups have since. The correlations exist. They violate Bell's inequality, which means they cannot be explained by any local hidden variable. The electrons are not carrying hidden information. The correlation is real and it's non-local. Now, this doesn't let you transmit information faster than light. I want to be very precise. You can't use entanglement to send a signal. But it tells you something profound. The description of those two electrons cannot be a description of two separate objects. Entangled particles are not two things with a relationship. They are one quantum system that happens to be spread across space. They are, in a very precise sense, still one thing. That's not Wheeler's one-electron universe. But it's in the same spirit. The universe resists being carved into independent, isolated pieces. Every time we've tried to fully separate things, conceptually or physically, the mathematics won't quite let us. The fields overlap. The entanglement persists. The boundary between this electron and that electron is, in some fundamental sense, not as sharp as we draw it. Where does explanation end? Here's where I'm honest with you. Why do fields exist? I don't know. Why does the electron field have the properties it has? That specific mass, that specific charge. We can measure them. We can't derive them from something more fundamental. The standard model takes these numbers as inputs, puts them in by hand. That's not an explanation, that's bookkeeping. Why does the universe have matter rather than antimatter? Unsolved. Why does quantum field theory, which works spectacularly well, refuse to incorporate gravity? Unsolved. Why is there something rather than nothing? Why do fields exist at all rather than a complete absence? I can tell you what physics says. It has no answer. That's not modesty. That is the actual frontier. The equations describe the behavior of what exists. They don't explain existence. But look at what we do have. From Wheeler's wild one-electron idea, we've arrived at a picture where the universe is made of a small number of quantum fields, and everything, electrons, protons, photons, you, me, the planet, every atom in every star, is a particular pattern of excitation in those fields. Your hand isn't a collection of 1028 electrons. Your hand is a configuration of the electron field, shaped by the electromagnetic field, held together by the quark field, giving you mass through the Higgs field. Those fields don't live inside your hand. Your hand lives inside those fields, along with everything else in the universe. Wheeler's idea was probably wrong in its literal form, but it was pointing with remarkable accuracy at a universe that is far less fragmented than it looks. A universe where separate particle is a useful approximation, not a fundamental truth. You look at your hand and you see 10 trillion electrons separate and distinct. The physics says, look again.